Ever wondered how a computer could harness the strangest laws of physics to perform calculations beyond the reach of today's fastest supercomputers? That's exactly what quantum computers are built to do. Today on Knowledge Hub, we're breaking down how quantum computers actually work. In a classical computer, everything comes down to bits, tiny electronic switches that are either a 0 or a 1. But a quantum computer replaces bits with qubits, which are built on the principles of quantum mechanics. A qubit isn't restricted to being just a 0 or a 1. Through a phenomenon called superposition, it can exist in both states at once. Imagine flipping a coin. It's not just heads or tails, but both, until you look at it. This allows quantum computers to process vast numbers of possibilities simultaneously. But superposition is only half the story. The real power comes from entanglement. When two qubits are entangled, their states become linked, so that measuring one instantly tells you about the other, even if they're far apart. This creates a web of correlations that lets quantum computers handle incredibly complex operations in parallel, giving them an edge in problems like factoring huge numbers, simulating molecules, or optimizing large networks. Building these qubits is no small feat. Companies like IBM and Google use superconducting circuits, microscopic loops of wire cooled to just above absolute zero, where electrical resistance disappears and quantum effects dominate. Others, like IonQ, use trapped ions, individual atoms suspended in electromagnetic fields, controlled with laser pulses. There are even experimental designs using photons of light or defects in diamond crystals. Each approach tries to balance stability, scalability, and control. And here's the challenge. Qubits are fragile. Tiny vibrations, stray magnetic fields, or even a hint of heat can collapse a quantum state instantly, an issue called decoherence. That's why quantum machines need cryogenic cooling systems, electromagnetic shielding, and error correction techniques that spread information across many qubits, so that mistakes can be detected and fixed in real time. So, why go through all this trouble? Because quantum computers open doors which classical computers can't. They could break encryption methods that secure the internet today, simulate the behavior of complex proteins to accelerate drug discovery, design advanced materials like superconductors or ultra-efficient batteries, and solve optimization problems in finance, logistics, and AI. While today's quantum computers are still in the noisy intermediate scale stage, limited in qubit count and accuracy, the progress is rapid. Researchers are pushing toward fault-tolerant quantum computers that could one day reshape industries entirely. If you enjoyed this deep dive into the quantum realm, don't forget to subscribe, because here at Knowledge Hub, we make complex tech simple and fascinating. And as always, stay curious.